Okay, so sorry for the delay. All right, so today is the last lecture, so I want to do two things mainly. One is to discuss quickly, very indicatively, what happens. So far in the first three lectures, we discussed how to do predictions at 3 level and dimension 6. So I want to briefly comment on what happens if one wants to go to higher orders. And then the other thing that I think is going to take most of this lecture really is telling you about the automation of this prediction. So a lot of progress has been made on the technological side, let's say, to automate these things. And also maybe show you a bit of phenomenology. So like just so you have an idea of what is the status of the fits, more or less, how many of these things have been constrained, so kind of close up with the interpretation. Okay, so when we talk about higher orders in SMEFT, it's never clear what we mean because there are many expansions, mainly two. There is the FT expansion, so we have been talking about dimension 6. We might want to go to dimension 8. This is something that people are exploring recently, so it's something that is kind of, I don't want to say popular, but so of interest in this particular moment. The dimension 8 basis was, two dimension 8 bases were published in 2020, so this is a relatively new. And with that, people are now starting to make the predictions. I'm not going into much detail about this because so doing the calculations will be complicated, but I think you got the point of all the things that would be needed. So you need to have the dimension 8 basis and to compute everything, so all the interference between the standard model and single insertion of a dimension 8 operator. So essentially what you want to do is to go to order 1 over lambda to the 4th, right? So one thing that you will need is the interference between the dimension 4 and the dimension 8. But this thing will contain a bunch of terms. So one is really dimension 8 vertices that are dimension 8 insertions. But then there will also be double dimension 6 insertions, right? And also the interesting things of insertion of dimension 6 square terms that come from expanding to quadratic order all the stuff that we have done so far. So all the redefinitions, renormalizations of the fields, definition of input parameters, and so on. These, in general, will also produce terms that go like C6 squared. So you might have single vertices that go like that. So if you have, I don't know, some sort of, just to visualize something, some sort of Drellian process, at dimension 8, you will have some dimension 8 diagrams. So you will have dimension 8 correction to the vertices, which in general can either go like v over lambda to the 4th, or they can go like v squared momentum squared over lambda to the 4th, or momentum to the 4th over lambda to the 4th. So you can have even higher enhancement depending on which vertex exactly you have. Different kinematics might be involved. Then you can have the 2 dimension 6, right? So you can put two things, one here and one there. And then you also have the option that, so you actually take one of these vertices to be standard model, but then the guy that you have here goes, I don't know, for instance, like CHD squared over lambda to the 4th, where this guy is a dimension 6 operator, but you have terms with the dimension 6 squared in the Lagrangian because the way you define the inputs or any other renormalization that you have done comes about. So there is a code that is called SMEFT FR that was produced by the group in Warsaw. Now, I don't have the archive number, but if you Google it, you find it immediately. They have recently released a version where they have this stuff implemented for the full Warsaw basis. So the first dimension 6 is called Warsaw basis. For dimension 8, the typical one that is taken is the Murphy basis, from the name of the guy that wrote this basis back in 2020, which is done with a very similar algorithm than the Warsaw one. So removing all the possible derivatives and so on and so forth. Yeah, so there are a few phenomenological analyses that use this, but as you can imagine, I mean, you already have your 2,000 plus parameters at dimension 6. So when you go to dimension 8, things don't improve at all. If you remember the graph that I showed you, for 3 generations in general, you have over 36,000 parameters. You never really have 36,000 in a calculation, but still this adds a sensible number of degrees of freedom. So there are a couple of analyses that do it selecting here and there which kind of operators you want to look like, or they do it for a specific BSM scenario. So you choose a simplified model, you do the matching, so you know which operators you need to care about, and you motivate your selection in that way. And the goal is to test if this effect can be sizable in LHC processes. And it is a bit ambiguous to verify if it is. There is no general answer. It depends on the process, the operator, the BSM scenario that you have in mind. Sometimes it can be that they can be sizable in the fact that, in the sense that including them changes the dimension 6 result quite a little bit. But this is something that is really under exploration. There are only very few papers right now. Something that you might see around in the next years. Okay, the other expansion that you have, obviously, is the one in loops. So you could, let's say, stick to dimension 6 and go to loops. I mean, you could do both, right? So in general, you have your dimensions, 6, 8, 10, and so on. And then you have your 1 over 4 pi squared some power. So 4 pi to some power, 1, 2, 3, 4, 5. If you stick to 3 level, you are here. This is what we have done. You can go to 3 level dimension 8, or you can decide to go 1 loop dimension 6. If you do both, you're looking for trouble and complications. No one has ever done it yet, so this is kind of combines the complications of both things. So the word of NLO corrections to SMEFT is very broad, and disclaimer, I'm also not the biggest expert in it, but still I think I can do it a couple of pointers, so this could take a course by itself, okay? I can give you a couple of pointers about what happens at 1 loop. At the level of the predictions, just so that you keep in mind what happens in the end of the day, what happens is that at 1 loop, you bring in a lot more operators. So for instance, if you imagine a simple process like x to gamma gamma, right? So in this SMEFT at 3 level, you basically have only that diagram there. So this happens at 3 level in SMEFT with an effective operator put like that. So this is a Higgs and 2 photons, for instance. And if you want to go to 1 loop in SMEFT, you're going to have a lot of things. So you can even have like the Higgs self-coupling that interacts here. Well, this is also a standard model diagram, right? So this already exists, but you can have other things. So you can have fermion loops, where here you might have dipoles or other operators. You can have specific diagrams in the SMEFT, like for instance, something like this, where here you have a dimension 6 contant interaction between 2 fermions, 1 photon, 1 Higgs, and then you have other vertices. So you can have a long series of diagrams, and you see that here you go from like one combination of 3 operators that come in to having, I don't remember the exact number, but like 15 different operators that now can suddenly enter. And this is for the simplest process ever, which is also quite constrained by the fact that the photon, because of gauge invariance, does not, so its interactions are not modified a lot. If you put Higgs to ZZ or WW, the number increases significantly because you have more freedom to break like left from right interaction separately, or custodial symmetries, and so on and so forth. So why do you need to go to NLO? Well, okay, one reason to go to NLO is to have increased prediction. So you can either have processes that exist, let's say, at 3 level in SMEFT, like this one here. And in this case, your prediction is going to look like some coefficient I, and then you will have some other corrections that come at order 4 pi squared suppressed by some power. So you Okay, you will have numbers in front, of course. So you have a leading order prediction, and then you have a dependence on some other guys that is suppressed. So let's say that if you're interested only in figuring out whether you have a deviation or not. So if you remember the two challenges that I mentioned yesterday, there was a challenge of being sensitive to these effects, so recognizing that you have an anomaly. And the second challenge is to actually assign the anomaly to the correct Wilson coefficient, so have a correct interpretation. So if you're interested only in the first thing, so just being sensitive to, do I have a deviation or not? Well, the leading order will be enough because you will already find some C different from 0 if you have some disagreement with the standard model, and you can be happy like that. The NLO becomes relevant where you really want to make sure that it's really this operator that is causing it and not some other kind of new physics running in the loop. So it is clearly a higher resolution, let's say, in the calculation. Then there are also processes that do not exist at tree level. So the loop order is the first one. At which they are generated, or in many cases, the loop order is the first one that interferes with the standard model. So for instance, if you have TT bar production, so in the standard model, you typically have it, imagine that it's, I'm thinking about the QQ initiator, okay, so you have the two quarks that go to TT bar, so it could be UU bar that go to T bar T. And in SMEFT, you have a bunch of 4 interaction points that do exactly the same thing. So you have 2 light quarks and 2 tops. And you can have several types of operators depending on the chirality contraction, the color contraction, the SU2 contraction. So what you have here is that if you're doing TT bar, the 2 currents must be in a color octet contraction, because in the standard model, they interact through a gluon, right? So there is a Gell-Mann matrix here and one there. So if you have an operator that is a color singlet with the 2 currents, this will not interfere because the trace of the color generator goes to 0 trivially. But if you start adding one loop corrections, this can introduce a small because it's loop suppressed, but okay, still one loop in QCD, so not too small, but it can start introducing a correction to the interference term, so suddenly it is non-vanishing. Something similar happens with chiralities to some level, so if you have chiralities that really go to 0, if you add an NLO correction, sometimes it's possible that you generate a non-vanishing interference. The other thing that happens at NLO, which is very important, is that you have RG running. So I'm going to write it down first, and then I'm trying to give you a sense of what this means in a bit of a bigger picture, let's say. So the RG running is trivially, I mean, it's like for any parameter of the standard model, but now you have many. So you have the RG equation where you have these coefficients I, and then you have an anomalous dimension matrix, gamma, that relates them to Cij. So you have to think that this is a 2499 cross 2499 matrix. It is well calculated. That contains, so it contains powers of, I don't know, like g squared over 4 pi squared. So dependence also on standard model parameters and so on. You can solve it, and you can calculate the correction. Technically, there should be here also a piece that goes like, so there is some, okay, some gamma I5 that goes like the dimension 5 coefficient squared, in the sense that, if you remember what we said, one of the first things, when you have 2 insertions of an operator of a certain dimension, the counter term comes at the double that dimension, right? So if you have 2 insertions of the dimension 5 operator, the counter term that you need to fix it is going to be dimension 6. So inside this matrix, in principle, there is also this term here. Now, because this is the Weinberg operator for Majorana masses of neutrinos, it's violet lepton number and so on, this is almost never relevant. Okay, so in first approximation, you can decide to set it to 0. And typically what is considered is only the linear dependence on the dimension 6 on themselves. So this matrix here is not symmetric and is not diagonal. It does have blocks. It does have a lot of zeros that can be understood in the most fancy ways that I will not have time to cover, but there are many symmetries and relations that the people are digging out to explain those zeros. It is not symmetric because in general, so you have one operator that runs into another. For instance, one easy case is the one of gluon fusion of the Higgs, right? So you have gluons here, you have a top that runs in the loop. And you might have an operator here, which is called CTG, and this is the chromomagnetic operator. So the operator is G mu nu with a color index, and then you have a Q bar, sigma mu nu, the color contraction, and the top. Okay, this is the left hander, and this is the right hander. So you have a dipole with a gluon that comes out. And if you put it in, this guy generates a divergence that runs, so it needs a counter term that is the contact point, which is generated by the operator CHG, if you are in Warsaw basis. So CHG is the guy that is G mu nu H dagger H. So this is the guy that produces gluon fusion at 3 level. And this is a correction to the loop level. So if you start putting in operators in your loops, you will see the CTG runs into CHG, but the opposite does not happen because you never have a situation where this vertex generates a correction to the TT gluon vertex. But CTG runs into something else. For instance, it can run into the Yukawa coupling. Now, I'm not 100% sure of the diagram, but I think it's this. Okay, and then you can probably have also another diagram which has two tops, the Higgs, and then there is a gluon here. Now, I'm not 100% sure if this contributes, but so the CTG operator gives you both this and this. And the combination somehow is divergent in one of the two pieces. And the divergence is reabsorbed by the correction to the Yukawa coupling, which is CTH. So this guy runs into CHG and CTH independently, but the opposite is not true. So that if you build a matrix of who runs into what, you will have entries that are off diagonals and then zeros on the other side, for instance. Okay. So this to say that this is an important effect that comes about. I can try to give you a sense of what this means at a bit of a more fundamental level. It would take a bit of a lengthy calculation, and I don't want to take too much time for this today, but to give you a rough sense, the idea is that if you think that you have some loop in the UV, for instance, think that you have an easy loop where you have one light field and one heavy field, and then they will be attached to, I don't know, some other lines on one side on the other. This is not important. So you have one that is heavy and one that is light. So your loop diagram, and do it in D dimension, will be something like this. This is a 2 minus m squared. Typically, when you do EFT, you do all the loops in dimensional regularization. Sometimes you will see people putting cutoffs, but this is not nice because in many cases the cutoff breaks the power counting. So if you solve this integral with a cutoff, you will find out a spurious dependence on lambda, which is not physical. So the thing that is typically done is that you do it in dimensional regularization, which is a scale-independent regularization. And you will find an expression for this diagram that, okay, we'll have the divergence and several terms. One of the terms is going to be a log of the light over the heavy mass. I don't want to give it. That, okay, is multiplied by a factor in front, okay. This is a 2. And you will also have a log of the heavy mass over the renormalization scale and a bunch of other finite terms. And if you think instead of doing this in the FT, okay, this is not what you do technically, but what you think that you are doing in practice is that you do the thing that we saw on the first day of taking the heavy propagator and expanding it out. So this becomes a 1 over m squared, 1 plus k squared over m squared, and so on and so forth. So relative corrections in momentum over mass, okay? So you expand this guy, and you do it before doing the integral. What you get out, so say that you repeat, so essentially you take this factor, you replace it by that, you take the integral, you do some simplification, and what you should get out is that you have some other minus 1 epsilon plus some finite term, and then you get a log of the small mass over the renormalization scale, and everything is multiplied by this guy. And if you compare the two logs, so what is happening is because you are doing the FT expansion, so you are removing essentially the non-analyticities in the initial theory. So the log of the mass square that you have here is an analytical function in the heavy mass, and this is exactly the thing that you are removing. So the heavy mass does not appear in the logs anymore in the FT. You only have it here because it's part of the power counting suppression. The only thing that you remain with is powers of the light mass and this new renormalization scale that you have there. Now, if you do the exercise of comparing the two expressions that you get, I mean, I realize that I should do it in more detail. If you're curious and you want to do the calculations right, you can check the Manohar lectures that are in the slides that I will give you. So you will have all the right factors, the signs, and so on and so forth. So if you compare the two, essentially you can realize that one of the things that happen in the going from the UV to the EFT is that this log here, which can be very large if you are in the limit where there is a large separation of scales, essentially you are splitting it into a log of the light scale over the renormalization plus the log of the renormalization over the heavy mass. So you're kind of separating the two scales by putting another scale in between. This part will remain in the FT, and it's this one here, and it's the one that you kind of have to treat when you do the RGE evolution. And this part here, which is the log of the renormalization over the heavy mass scale, is actually the matching contribution. So if you want to calculate what does it mean to do the matching in this case, you have to take the difference between these two integrals, and you really realize that the difference between these two in the finite parts is going to be proportional to this quantity here. So what you're doing essentially is that you had a theory that you could have used down to arbitrarily small energies, right? I mean, nothing forbids it from using the UV complete theory to calculate everything down to super small energies. But if you do the exercise of integrating out the heavy particle, essentially becomes a theory where you have a matching contribution that takes part of the non-analyticity in the heavy mass that you had in the original loop, and then covers the rest of the evolution with just the evolution in the FT, where you only have the light mass scale and the renormalization scale that goes down to the low energy. And in doing this process, you got rid of this quantity, which can be very large. So in a sense, you have resummed the logs and gotten a theory that is more perturbatively convergent than the full theory when you evaluate it in the low energy, because you split in these two things. You can also decide to choose a renormalization scale that is equal to the heavy mass, and this will kill the log and will give you a small matching contribution. So this is part of the reason why we said the thing that when you have a UV theory, you do the matching at the lightest heavy mass. So you kind of minimize the matching logs, and then from there, you just take care of the running in the EFT, and you have the separation of scales that moves down from there. Very indicative. If you want to have the more details, check the lectures, because it's going to be explained better and more step by step, and probably will click more. But this is really the conceptual action of the separation of scales that happens in the EFT. Okay, so I can give you a few examples. So another message is maybe you're interested in how to normalize this theory. Of course, I will not have time to do that. But another message that appears here is that the counterterm structure, so really the divergent structure of the UV theory and of the EFT, have to be the same in the infrared, but they have to be different in the UV. You don't really see it here, so trust me, in this case, you see that the two 1/epsilon terms have a different coefficients. This one comes with this combination in front, and with a minus, this comes with 1/1 epsilon, so they really have different coefficients. In this case, it's only a UV divergence, but if you do the exercise of splitting the UV and the infrared, and you do it carefully, you will realize that the infrared structure is the same in both theories, but in the UV, they really have different divergences. So they're really different theories, so you need to introduce different quantities to take care of the various UV divergences, let's say. I'm thinking what I was going to say. Yes, so this is what happens when you renormalize it. When you do it in SMEFT, so really from a bottom-up level, so you go back to the idea that you are working with your dimension 6 Lagrange, and you forget all the fundamental thing, and you just want to start bottom-up and calculate. There is a bunch of other things that you have to address, and that I will not have time to cover, but you can be aware of them. So for instance, we saw the other day that there are these operators that create some mixing between the gauge fields. Because we were working in unitary gauge, we kind of oversimplified a bunch of calculations, but if we took care of working, for instance, in Feynman gauge or in another gauge that is more suitable to do loops, we would have realized that there are operators that mix also the Goldstone bosons, the same ones that change the kinetic term of the Higgs. They also introduce some mixing between the Goldstone bosons, so you have to take care of realigning the two components when you do the loops. You need to take care of defining a proper gauge fixing term that is consistent with these assignments. It's something that has been done in the literature, but it took a bit. So in particular, the rhetoric sector is significantly more complicated than the QCD one. So I just want to show you some results to give you a qualitative sense of how this goes. This is an example from a calculation of the Higgs to VV bar decay that was done by the group originally in Durham along the years. So this is their final papers where they collected all the various contributions that they computed. And this is the width calculated at SMEFT, normalized to the standard model at leading order. So both of them at leading order, but taking into account the running and mixing of the operator. So you can decide to have a 3-level calculation, but where you keep track of the running of your EFT couplings, and this will give you, in a way, a leading log estimation of the NLO correction, okay? So for the moment, this is the leading order, and you see that there are a bunch of terms that you should also recognize already. So if you remember the Feynman rules that we drew the other day, one of them was precisely one of the Yukawa interactions. Okay. And we said that this is ABB. This was going to be the Yukawa of the standard model. And then there was 1 plus the delta kappa H correction that comes from normalizing the Higgs wave function. And this contains the operators CH box and CHD. Then there was the correction of the VEV, and then there was a direct correction of the interaction. Now, I hope that I got the signs right. So this is the direct vertex contribution from the operator that corrects it, and this came from the input parameter choice. So if we have G Fermi as an input, this contains the operator CHL3 and CLL prime, because G Fermi is extracted from the muon decay, so this is what we are doing. Yes, by the way, so this is there, even if this thing doesn't depend on V, because we're assuming that the Yukawa couplings are determined from the masses as inputs. So in the operation of going from the mass to the Yukawa, we subtracted a V, and this propagates to here. So you should see some of these contributions around here. So there is the CH box that comes from the delta kappa H. There is the CHD. This is the direct Yukawa correction in CBH. It has a minus. There is this guy that also enters in all the input corrections. And these are all interactions that are generated at one loop. So they enter through the running of the guys that contribute at a leading order. So you see that these contributions in this unit, so I think that their C tilde is like our C bar. So C tilde here is C times V squared over lambda squared. Numerically, if you put lambda to 1 TV, this is 0.06. Okay, so if you put lambda to 1 TV, the V squared over lambda squared is 6%. So now you have a number in front which is of order 1, but then you have to think that in terms of the dimensionless Wilson coefficient, this has to be multiplied by 0.06. Okay. So these things are of order 1, so 3, 2, 1, and so on, and these are smaller. These are of the order of a few percent or tens of percent. Then they also went and actually did the calculation at NLO. And this is the series of operators that contribute. You see that it's a much longer list. You have some things that are 4 quark interactions, because you can get diagrams of this form, which are a big curse. So here, typically, you have the top, and then so you have top here and B there, right? So this is a TB-TB interaction, depending if it's left-handed or right-handed, you have QT-QB, or another piece that now I'm not seeing. You can have dipoles that enter and so on and so forth. And then they have the operator that brings in the gluon coupling to the Higgs, which is quite different from the estimate that they got from the leading log. So they're also interesting behavior. Now I don't see it anymore. Okay, anyways. So you have one large contribution that comes in from a guy that is produced at one loop, but because it's the coupling with gluons, it has some QCD enhancement. Even if it's loop suppressed, it is actually of the same order, if not bigger, than the contributions from the other operators that enter at 3 levels. So this is another phenomenon that happens, and we need to worry about sometimes. What else did I want to say? Yes, so about the impact of DRG running and mixing. This is something that's a bit under development. So DRG has been calculated 10 years ago. Okay, so the DRG of the dimension 6 was one of the very first results that started the technical development of SMEFT in the last decade, let's say. So that has been done. It has been automated, implemented. There is a code that is called D6 tools that, if you want, runs everything, solves the DRG equations for you, even with favor indices and so on. The next challenge is really to include this running inside the predictions and take care of them properly. So the thing that you should do, the way that the physics interpretation should go in principle, is that one essentially fits the Wilson coefficients defined at a certain scale. So we have to make a scale choice. Say we define the coefficients, for instance, in that case at 2 TV. And then essentially we calculate the predictions for any other process, running every time the coefficient from the 2 TV to the scale of the process that we're interested in. So the prediction will include this bunch of running, and every time we do the fit, we're really bringing back to the reference scale, right? So this is something that has not been done a lot so far. there is not even the technology. So it is done for a few things like later week PO. It can be done because you know exactly what the scale is and you can just compute the running using some numerical tool, and then everything happens at the same scale and you can just calculate there. But it is more challenging for processes at the LHC that have a kinematic distribution that spans 2 TeV. For instance, TT bar production. So in principle, if you have a TT bar distribution that starts at 300 GeV and ends at 2 TeV, those could be different scales at every bin. And to do this, you need to really implement this running or find a way to keep that into account in your calculation or in your Monte Carlo concretely. So there are some people that are working on this. So this is an example from a paper of just not even 1 year ago from the group in Manchester of Eleni Veronidou and so on. And they have been trying to do the first studies. So you first see here what happens if you have one particular coefficient. So for instance, the CTG that I drew before and now I erased. So the chromomagnetic top dipole. You fix it to 1 at 2 TeV. So what you're doing is this. Right, so you decide that at 2 TeV, this coefficient is equal 1 and the other coefficients are equal 0. And then you evolve going to lower mu because the operators mix to each other. And I told you the CTG mixes into the Yukawa, which is this orange guy, and in the C5G, which is the purple one. It means that even if those initially were 0, they will be produced with non-zero value as you go down. And this is in fact what happens. So it produces the Yukawa that sits here and these other coefficients that sits there. This looks smaller, but really depends on how you normalize the operator. And something similar happens also in the sector of the 4-quark operator. So the 4-quark, they're all coupled to each other. So you can start with something that has a color singlet with 2 light up quarks and then a heavy left-handed doublet. You put it to 1 and 1 TeV, and then you will see that what it does is that it mixes in the octet. This is the singlet that mixes into the octet. So this is one of the things that makes the singlet gain a non-zero interference as it goes to lower energies, even if you didn't have it at the beginning. So this should suggest, and it's something that has been well known for a while, that a very nice, interesting feature of the SMEFT is that if you try to restrict to one operator, it's very hard. So there are very few cases, or probably even none, where you can say that you have a theory that produces one operator, and then as you go to lower energies, you still have that one operator. So most of the time, the moment you have one, it will produce a bunch of others as you run to lower scales, which kind of makes more the case for trying to use as many as possible of those, and is also kind of worrisome for the interpretation, so it makes things significantly more complicated. But so we have the formulas to take this into account, let's say. Yes? Sure, yes, it's just a matter. It should, but I mean, the technology has to be developed. Yeah, I know.
I mean, in most of the cases, because I see this running things is only
Yes.
reservated. So what people does fix this?
They fix it. Yeah, they do the thing that we did the last 3 days, right? So you say this operator is C, you ignore the scale dependence. If you're calculating 3-level, okay.
But since big, this scale dependence.
Yeah. sometimes the operator flips sign.
Okay, but then
No, okay, no, but it's not useless. So, okay, the point is you do your calculation with your coefficients. Implicitly, if you're not specifying what the coefficient is, it means that it's the coefficient evaluated at the scale of the process. You have the problem when you want to combine different measurements and have a coherent interpretation, because if you have a measurement that is done, so if you have a TT bar measurement is done at the LHC, and then you want to measure something else that has these operators but leaves at a much lower energy, then the operators for TT bar are not the same operators for the low energy, and you need to take that into account when you... So in most of the time, the running is also relatively small. So this is large because these are the QCD operators, right? So they have octets, they have gluons, so there are factors of alpha S that enter in there. If you have only the electroweak sector, The running is not so huge, depends, okay, the normalization of the operators is arbitrary as well, so factors of 10 or 100 easily come and go. But yeah, so there's a technical complication in really accounting for that. So this is the result that they get for a concrete process. So this is you don't see it, but okay. So this is the MTT bar distribution that goes from 300 to 2 TV. This is for one particular operator. So these are 2 4-quark operators. So there are 2 of these. One has the top right-handed. So this guy right-handed, this guy left-handed, and then the color singlet. While the other one has the 2 chiralities flipped, and sorry, this is a color octet, the first one. And the second one has the chiralities flipped and the color singlet. Okay. So in one case, you see that the predictions that they have bin by bin. So what they do is that they have a prediction without running, which is the blue. So you just naively take your operator and you put it in, you ignore the fact that it runs. Or in the other case, they have the red line for running it with a scale that is ht/2, or with a scale that is mt. So yes, okay, so they assume that from 2 TV you go down to MT and you keep it fixed, while in the other case, this changes bin by bin in the red case, the scale at which we're evaluating. So blue is not running, yellow is I run from 2 TV to MT, but then I keep it fixed, and red is I vary the scale bin by bin. And I say that it's ht/2 calculated in MATLAB. And in one case, the results are not so different from each other. Okay, there's still a few % difference that you might care about if you want to do really precision calculation. But in the other case, the running really makes a huge difference. And this is precisely because this is this operator. So you started off with an operator that is a singlet. So if you ignore, so if you just take it face value, it doesn't interfere. The interference is very small. It's 2% that you see here. But if you take account the fact that it runs into color octet, and the color octet does interfere much more. And so you can have these sort of effects. This is, okay, the first study that really came out dedicated to this, so state of the art. Progress will be made. So it's not always this dramatic, but this is the poster case for, yeah, maybe we should run. Okay. All right, so this kind of closes this part about the loops. If you have any questions about loops, try to ask me, even though it's not always easy. Otherwise, I will go back to 3-level quietly and tell you a bit more about the automation and maybe show you some Fino. Okay, we can take them also later. All right, so automation. So we have been doing a lot of calculations on the blackboard, but really the way that predictions are done, especially for collider physics nowadays, is through Monte Carlo. Okay, so what is used for SMEFT typically is MATGraph. MATGraph that now is also AMC at NLO, because it has a bunch of convenient features. So it's very flexible in terms of processes. It just takes a UFO model that you can give it, and then it will produce the diagrams by itself. You don't have to hard code process by process, so it really does the calculation of the matrix element for you. It has a reweighting model that I will tell you about in a second, and also for historical reasons, essentially. So most of the codes were developed for that. What you aim for when you do the MATGraph simulation, or like if you're an experimentalist, is to do this morphing, which is a fancy name for something that is quite basic, really. So the thing that we've been saying 7 times is that this is always a polynomial in the Wilson coefficients, right? So whenever you have an EFT prediction that is done at dimension 6, you will have an amplitude that is linear in the dimension 6, and when you square it, it will spit the standard model contribution, the interference contribution, which is linear in the Wilson coefficients. And then if you want, you can also keep the quadratic contribution, which is from putting in one operator and then squaring. So this structure means that whenever you produce an observable, a decay width, a cross-section, an asymmetry, anything, as long as it's not ratios of things, it will always have a polynomial dependency. It will always be a linear or quadratic polynomial. And this holds even if you're evaluating bin by bin. Okay, so if you have a distribution, each of the bins will have a quadratic dependence on the values of the Wilson coefficients. Just these prefactors A and B will be different bin by bin. Okay, it just because physics has to be this way, it doesn't matter if you put kinematic cuts, you're still squaring an amplitude that was linear. So the morphing is basically the idea of determining the prefactor of the polynomial for every single observable that you care about. So if you're trying to do a measurement and you have a distribution, you want to have this list of coefficients for each of the bins. And then with this, you can go and parameterize analytically, semi-analytically, the value of the predicted cross-section as a function of the Wilson coefficients, and then you can do a fit with a chi-square or with something else. Now, this is going to sound a bit redundant, and why? But believe me, a few years ago, this was actually something that was a realization, especially for the experimentalist, that because you know that the dependence has to be like this, the number of parameters that you have to calculate for each observable is 1 plus n for standard model plus interferences, if n is the number of operators that you have, and n times n plus 1 over 2 for the quadratics, which is much less than n squared, which is what the experimentalists do in a standard way. So whenever they have a model, and of course the model doesn't necessarily respect this dependence, they basically sample on a grid of points through all the parameters. So this kind of speeds up, even though not too much, the generation. And then once you have this, you can compose your prediction as you want. So there are two techniques that I used to simulate these things in general before we even look at UFOs. So there is one technique which is just direct generation. So you open MatGraph, you tell it I want this process, and I want to put in this operator. It will produce an event sample for you. That's your prediction. And then you repeat it again for another interference term, you repeat it again for a quadratic term, and then you have your bunch of simulations, and you can reconstruct the polynomial from there. The thing that is not super pleasant about that is that you will have a different sample for each of the terms of the polynomial, which have independent statistical uncertainties. So they are not always on the same page. So if you need, for instance, to have that two coefficients have exactly the same value in front, because it's really the combination of C1 plus C2 that enters in the prediction, this will be respected only up to the statistical uncertainty of the simulation. So I think that you can do as an alternative to that is to do this reweighting. Reweighting means it's used in many contexts, not just EFT, but in EFT is particularly useful. Reweighting means that you simulate once, you have all your events, each event has a weight that typically in the sample is unweighted, so the weight of each event is equal to the total cross-section, such that the cross-section is the average of the weights. And if you want to go, so you have a sample that is generated in some conditions, and then you can change the conditions by basically recalculating only the weight, which is calculated as a ratio of the matrix elements, and reassign it to the same event. So the difference in this case is that you create a new sample by changing how much each of the events matters in the distribution, but you keep exactly the same events in exactly the same phase space points. And this has the advantage that if you simulate, let's say, the initial sample is with the standard model, and then you want to go from there to the interference piece of one particular operator, you just recalculate the weight. The weight is exactly the ratio of the matrix element between the interference and the standard model squared. And so if you want to go and plot the ratio of the two samples eventually, it will be calculated exactly. So if you have an operator that really gives you 3 times the standard model for every single event, the ratio plot will be 3. While if you do it with 2 different samples, because of the statistical things, it will wiggle around 3. And sometimes you don't know. Now, the reweighting is not perfect either, because, yes, because to reweight an event, you have to have it. And sometimes you don't. So if you have, it depends where you start from. So if you start from, let's say, a standard model sample, which does not contain events in a particular region of the parameter space, typically in the high energy tail, because the standard model dies off. And so you will always have a bin where you don't have an operator here, but you would have it if you had the operator, because the operator maybe is momentum enhanced. Then you have a problem, because if you try to reweight the initial sample to get the new one, you would need to create an event that you don't have. So you will still find the 0, but the 0 kind of reflects the absence of sampling of the parameter space that you had at the beginning. Now, this is easy to imagine for kinematic distributions, but it happens for more subtle things. For instance, for a specific color contraction or for a specific helicity configuration of the final state. Sometimes you generate in the standard model, it gives a certain helicity configuration, and then you want to add an operator that has a dipole, it has a p-violation, it has something else, and depending on what kind of reweighting you do, if the reweighting cares about the helicity, it will not find the helicity that it wants to reweight and will give you 0 when actually the 0 is not. So anyway, you don't need to worry too much about this now if you don't have to do an analysis, but this is the kind of issues that are around when you want to do SMEFT in practice, let's say. Okay, so I told you that typically people use MATGRAPH. MATGRAPH generates anything with anything, so you just need to tell it what's your model. And the way you tell it what's your model is that you use a UFO model, which stands for Universal Fine Rules Output, that you might have seen around. So in principle, UFO models are also taken by other Monte Carlo, so it's meant to be universal. And there are a few UFOs that have been produced in the years. So one of the earlier ones was DIMSIC-TOP. Well, actually, there have been many earlier prior that didn't have complete bases, so they had partial bases, a few operators that were relevant, implemented here and there. Then there was a phase where people started to try and implement the whole bases in order to have a consistent tool. So DIMSIC-TOP was one of the first where they implemented all the operators that contain a top quark. So they modifies an interaction of the top quark, which, okay, is a choice, but they did it in a very complete way, including also flavor change neutral currents and all sorts of complications. And then more recently, the two ones that are being used the most are SMEFT-SIM, which is for leading order, and SMEFT at NLO, which is designed for one loop in QCD. One loop electroweak doesn't exist. It is in the making. I have no idea how long it will take, but it is a significant complication also. I mean, already the MATGRAPH ground for doing one loop electroweak is relatively new. So this is all a recent development. So I will tell you some few words about SMEFT-SIM because it's the one that I made. So I think it makes more sense. But I can tell you first, so to give it justice, about SMEFT at NLO. So SMEFT at NLO has a point that wants to do one loop QCD. So this is their target, that's their design. And they have the complete Warsaw basis, but they need to introduce some simplifications because otherwise it would be impossible to simulate, and you will have a lot of unnecessary details that complicate the simulation without adding much. So for instance, they work in a 5-flavor scheme, so they keep the bottom quark massless, which removes a bunch of loops. So the only loops that there are those of the top. And then, as we discussed yesterday, if you ignore CKM mixing, because everything is massless except the top, you might as well work in a flavor symmetry where you have a U2 for the two up-type quarks, so the left-handed doublet and the right-handed up, and the U3 for the down quarks. To add something more, to do it a bit more general, they actually simplify the thing of the leptons. Now, technically, the group is a U1 vectorial, so the same U1 for the left and right-handed part for each of the fermion generations, so a U1 cube. It's a detail. The point is that this forbids lepton flavor violation, but it allows violation for universality. So you can set independently the coupling of the muon and of the electron, but you cannot have mu to E conversion. So it's one of the assumptions that they put in. And this is used a lot. So this is the standard tool for top quark analysis, for instance. So if you do TT bar production or single top, you are really interested in one loop QCD corrections. And so SMEFT contributions to that. Also, if you do gluon fusion for the Higgs, you're interested in that. So this is really what you might see around. SMEFT-SIM was designed originally for leading order. I mean, it is still designed for leading order, but because it does only 3 level, then it has a bit more flexibility to play around with another not always relevant things. So we decided to keep all the possible flavor indices. We actually have a bunch of flavor versions, and also, like, you can have a complete dependence on the CKM, on the fermion masses, and all the possible refinements that would make the one loop overly complicated. Quick slide to say, in principle, there are other Monte Carlos that are around. So if you are familiar with any of these, be aware that this can also do SMEFT in some conditions. So PowerHack has a few NLO calculations implemented, NLO QCD, which are those I see here if there are no updates. But yeah, you need to hard code them. So you need to calculate first and then put them in. Sherpa in principle supports UFO as well, but I've never seen analysis done with that. And then there are a couple other codes that are used by specific groups for partially historical reasons, but that are used to do this kind of analysis and also to cross-check MATGRAPH results quite often. Okay, I don't want to put it too long as SMEFT because I'm not here to advertise, but I just want to showcase a couple of things. So this thing, so we talked a lot about flavor symmetries and about input parameters. So this comes in versions that implement different options. So there's a flavor general version. And then there's an MFV that you can forget about. The U3 to the 50 is the one that is the most symmetric one that we discussed the other day. And it's basically the default if you want to do bosonic physics. And then there are two options for the top. So they both use the U2 symmetry on the quark sector. So the top and the bottom are separated out, but they differ by what you do in the lepton. So the top does the same thing as MEFT and LO, while the top U3L keeps a U3 symmetry for the leptons, which is simpler. And it has these two options for the electroweak input parameter scheme. So what it means is that all the redefinitions that we have done in the last 3 days, they are automatically kept into account inside here. So technically, you don't have to do them ever again. But it is very important that you know where they come from, I think, because sometimes it's confusing. We found confusing examples also the other day of why does a 4-lepton operator enter in Higgs production, for instance. And so the reason is that this stuff is already automatically implemented in there. So I can go quickly here. This is the number of parameters that it has. It has also the propagator corrections. This is a bit funky, but it is there. So the idea is that if you remember yesterday, we said that when you have a propagator, you might want to expand out the correction that should be decently safe, at least for the decay width correction. And so what it does is that in the code, it has the normal Z boson that propagates with a normal propagator, and then it has a dummy field that propagates with just this, well, these times these blocks. So it has a field with a weird propagator that carries this correction. But in principle, so this can be simulated in there as well. It has a thing for loop couplings. Okay, fine. Sorry, I have to go quick because I want to get to the. Are we going? Oh, okay, to the Fino. Yes. No. No. Yes, but the NLO package is designed for QCD mostly, right? And you have this problem when you have the W's disease. For the top, you have it, but not so much. I mean, you wouldn't really put the propagator. I mean, you can do it for the top, but really the top, every time you analyze it, you treat it in there with, like, you only simulate top production and then you decay it after. Depending. Depending. But okay, let's say that this is what is usually done in SMEFT. It's not the best thing. So yeah, I mean, okay, for SMEFT, this was kind of a leap as well. It's not super ideal. It's also very confusing that, sorry, I didn't say it yesterday, but you cannot do quadratics with propagator correction. So where am I going? Oh, I skipped this. That was very important, sorry, because this is going slow. Okay, so this should come back here. So this is designed for a linearized correction. So you have linear corrections to the width, and you are linearizing out the amplitude, right? So for the interference term, this makes sense. But if you want to calculate what is the quadratic contribution to this, there are all sorts of issues because essentially you are facing the fact that the quadratics defined in the usual way are not the complete 1 over lambda to the 4th contribution, and it becomes really ambiguous what is the equivalent of the normal quadratic here and what not, because the operation of squaring this amplitude and of expanding out the propagator do not commute. So if you decide to expand first and then square the amplitude, you get something. square the amplitude first and then expand the propagator, you get something else. And on top of that, you don't know which quadratics you should put inside this delta. So the only answer at that point is to calculate the full over 1 over lambda to the 4th. So this is another thing that confuses experimentalists a lot, because they do the analysis for linear and quadratic. And for linear, they can put in the propagator corrections, and then they send me an email for the quadratic, and I'm like, no, you're putting in random numbers. But yeah, it's also not nice, because in one case you keep this into account, and in the other you don't, but it's really part of the ambiguity game that you have when you do the squares. All right, sorry, so I skipped one thing that was kind of important, because this could actually be interesting to theorists. Now, if this, okay. So there is something that is useful. There are a few tools, actually. So because SMEFT contains all these things that have already been done, the only limitation it has is that it's done in unitary gauge, because it's designed for simulation. But up to that, it basically contains all the SMEFT with all the features and done already for all the input specifically and flavor options specifically. And so it's nice to have a database that is human readable of the Feynman rules, so that if you want to go and do a calculation by hand at some point, you can just consult what this is and check which operator goes where and what does this look like and so on. So there are two things that are relatively simple. They were done, one by an experimentalist in Atlas and one in CMS, so they each took care of this thing. Which are two tools. When I send you the slides, you can click on this. They basically visualize this. So their question is always, okay, if I have this operator, in which vertices does it go? So typically, you can select the operator, and it will give you the drawing on which vertices it goes. And then there is this thing that instead is something that is more for theorists, so you might be more interested in. That it's basically a Mathematica notebook with a Mathematica package. You can go on this link here on the notebook archive and download it, and it contains this marvelous interacting game, if I can produce it. Okay. So it comes with a folder of things that you have to import, but it doesn't take forever. So you just import the information, and then you have two tools. One is the Feynman rules by operator, so you want to ask where does this operator go, and the other one is by vertex, so what is the Feynman rule for this vertex? So we can start from the second, and it will have, you see, some default thing that it pops out. You can write the vertex here, then you can pick which flavor assumption you prefer, which input scheme. You can decide to do some simplifications. For instance, if I remove the CP odd, all the tilde should go away. And it has a bunch of things for visualization. So you had a question about the triple Higgs coupling yesterday, and we can just ask it. Okay, that's this marvelous thing here. So it's written in the way that this is the standard model interaction. And then, so this is the relative correction. There is this piece, which is the delta kappa H that survives. This is the input correction. So if you decide not to use this specific input scheme, but to call it generic, it will tell you that this is delta kappa H, this is delta GF, and this is the direct contribution from the Higgs cubic. But then you also have the CHD operator that gives you the coupling with the momentum dependence. This I forgot. So this is not part of the scalar potential. It is, so the CHD and the CH box give you some momentum enhanced versions, and so you can read it off from there. And yeah, okay, so you can do also the same thing for the other, but okay, you get the point. So this is something that is there, and if it can be useful, it's nice. So for instance, you want to know where does CHB enter, and it tells you that it goes into the couplings of the Higgs to photons, photon Z, ZZ, and so on and so forth. If you're curious about the CTG, that only exists in the top version. A real part, because it's as complex. Okay. It will tell you that it produces a TT bar G interaction. We also with two gluons, with one Higgs, and two gluons. You have all the combinations, and you have all the weird Lorentz and color structures that you need to take care of. All right, sorry. Yes, this is enough for the advertisement. Okay, so I want to get in the last 15 to 20 minutes to the pheno part. These are the slides that I was rushing to make before, so I hope they are fine. Okay, so there are several sectors of productions in, so several sectors of observables that you can care about. Disclaimer, I am mostly focused on high energy LHC physics. If you talk to other people, they will probably start talking to you about flavor first. There's really different groups of people that are looking into different things. So I try to be comprehensive, but this will be LHC focused, let's say. So one sector is the Higgs and letter weak. They clearly come together for questions of gauge invariant. Typically, if you look at processes in the Higgs generator weak, what people mean by this is that you can have Higgs production and decay, and you can have diboson, which is the first electroweak process that comes to mind, and also, for instance, vector boson scattering or triboson or these higher multiplicity processes that are being introduced now. So the first studies are coming out in the later years, while diboson has been studied to death. And typically, if you want to be really leading order and minimal, you can restrict down to 20 parameters for the dimension 6 SMEFT. Not really for vector boson scattering. For vector boson scattering, I'm cheating because this process is really more complicated than it looks. It has a slight issue, which is that it has two tagging jets. So vector boson scattering in the standard model is this process here where you have a quark that goes approximately straight. Then something here happens. You produce two bosons and you have another quark that goes straight on the other side. So here you can have W's, Z's, or gammas in all the combinations that are allowed. And when you do it in SMEFT, you have all sorts of interactions that you can correct. But turns out the one that is particularly nasty is this one here, where you essentially produce the two final state bosons and you have a 4-point quantum interaction for the quarks. This is not the first thing that you think of probing when you do vector boson scattering, but it has a super large effect because given the kinematic selections of these two jets, that contribution is particularly large because it's not suppressed by any propagator in T channel or S channel or anything. It's really quite strong. And the point here is because at the LHC, you don't distinguish anything about the jets. You don't know the chirality, the flavor, the charge, nothing. You have 20, 30 operators that can enter. You can have color octets, color singlets, stuff with the up, stuff with the down, charge current, neutral current, left-handed, right-handed. You can have all sorts of combinations, and you're completely blind to them. So you have to cut down somewhere. Yes? You can also, yes, you can also combine with dijet. Yeah, so it depends on how picky you want to be. So the thing is that, so this has not really been done, but you could compare this with just dijet production. And then what you have in dijet is a bit different because in dijet, you have a different standard model diagram, right? So in dijet, you will mostly have color octets, or you can have like different charge combinations because of how the PDFs enter. While here you have specific charge, so depending on the channel that you have, so like if here you have same sign WW, then given that the PDF is arranged a certain way, the certain charges will dominate and certain chiralities only. So each channel really has a different combination of these guys. You will never have enough measurements to break them out, all of them. But yeah, so you can improve a little bit. You just have too many and you're too blind because you don't know anything about the initial state nor of the final. So you can combine several things, but so this is kind of, I don't want to say swept under the rug, but something that people don't know what to do about yet, apart from that. So VBS really has many more. But roughly, if you think only of the bosonic Higgs part, it's of order 20. So this is a picture of how things talk to each other. So you can have the same operator entering in many processes. And so the point of this slide is that there is a lot of crosstalk between different measurements and different sectors. So you have, for instance, diagrams for gluon fusion of the Higgs. This is vector boson fusion, VH production, and then you have TTH production, which is something in the top sector. And every time you see a dot with the same color, I hope no one is colorblind. If yes, I'm really sorry. It's the same operator that enters in several places. So you have this feature that things that produce a coupling of a vector boson to two quarks also produce the same thing with the Higgs coming out for gauge invariance. The same thing happens for the chromomagnetic that can produce the Higgs coming out of the TTG interaction. You can even have the TTH entire process produced by one vertex of the CTG operator. So there is really like a hard interconnection between things, which is one of the arguments for doing global analysis. So the message is really like, if you have one process, you can do very little. You can have a few combinations of things to be constrained if you have a distribution. So combining several things is the way to go to break down all these effects. So for Higgs, the main thing that is usually taken is simplified temporal cross-sections, measurements of production and decay. You don't really care about it. On the top sector instead, the typical things, of course, TT bar production. Also single top production is basically standard by now. And even TTV. So TT bar and single top, they are typically calculated at NLO in QCD. I don't have diagrams here, but SMEFT at NLO is used a lot for this. For TTV as well, but it's a bit harder to get. I mean, it is done only for the QCD and LO part. Well, so the electroweak part is not explored yet. And even here you see, so these are exactly the same colors as before. You already have some non-trivial interplay between the different processes. And these, especially the TW, TTW, and TZ production talks a lot to the electroweak sector. So it's again the same kind of operators that you have in the Higgs and the electroweak sector. So people started from doing the analysis of the top and the analysis of top of Higgs and electroweak, and then eventually they put them together. There are only two groups that did it because it's a lot of work and because you need the technology. So the fitting of these is many parameters and is highly non-trivial. So there is some kind of divide. Sorry, yes, okay. You also have some more interplay. Okay, you got the point already. So one of the groups that did this so far is the group of John Ellis, Veronica Sanz, and their collaborators. And the characteristic of their fit is that they only use linear terms, so there are no quadratics here. And it's already big news that with 34 parameters, the fit closes. So they don't have flat directions. They have enough measurements to constrain them all. There are bars of different color because they correspond to different flavor assumptions. And they have, so the orange ones is a fit of only the Higgs and electroweak sector, and then the pink red part is a fit of top Higgs and electroweak altogether. So there are a few messages that typically come out of plots like this. One is that there are hierarchies. So if you look closely here, there are some operators that are multiplied by 10. So which means that in whatever normalization they were defined, the constraints on these interactions were actually a factor of 10 larger than what is shown on this scale. And some of them are divided by 10, so it means that the bound is actually a factor of 10 weaker than what is shown in this scale. The other thing is that the constraints in the electroweak sector, that by the way contain also the LEP constraints, so electroweak precision observable measurements at LEP, are about another magnitude stronger than those in the top sector, roughly, for a simple question of precision of the measurements of the error bar, let's say. So electroweak POs still dominate this kind of fits, with a few exceptions. The two, let's say, LHC observables that compete really with that in terms of precision are Higgs production in gluon fusion and decay in gamma-gamma. Those are the two things that right now are already in the few percent level, and they really compete and give results that are comparable to those of electroweak POs. Everything else is a little bit more behind. Okay, I mean it's not bad, but it has a smaller precision. You can also see that everything is compatible with 0 because if you don't put the deviation in and correlations are okay, nothing comes out. The bounds here are of order 1 in a scale where lambda is normalized to 1 TV. So the target is to go below the 1. When it's below the 1, you're converging. And this is the case for most of these guys, not really for the top ones. And in fact, the top fit sometimes it's dominated by the quadratics. They don't have the quadratics here, so this is particularly weaker also for that reason. While for the Higgs and electroweak, it depends a bit on the process. But so for electroweak POs, the linear times dominate, if I'm not wrong. So this is the other case, which is the group of Juan Rojo, Fabio Maltoni, and so on and so forth. This is called SMEFT. They use a software that is based on the NNPDF software. So it's been evolved and transformed, dedicated to SMEFT, but it's a sophisticated fitting tool. And they do a fit that actually has quadratics, so this is a bit different, and has predictions at NLO and QCD, while the other one had only leading order. So they have a bit of a different range of operators. They're also reverse, so the electroweak ones are to the right and the top ones are to the left, and this scale is logarithmic, so it's not immediate to compare, but okay, everything is consistent with 0 here as well, and if you pay attention, it's like bounds are within the plus and minus 1 window, so this is starting to work, and for the parameters that go into the top fit, the bounds are a bit worse, but if you compare, so the yellow lines with the blue ones, so the yellow are linear only and the blue are linear plus quadratic. You see that for the electroweak part, the difference is not huge. Okay, we're in log scale, so it's factor over the 1, but the difference is not huge, so we are close to the region where, okay, we could do with the linear only, so the FT series is making sense. But for the top, the quadratic really dominates. So without the quadratic, some of these guys are really completely unconstrained. This is again the same. Last feature is the fact that things can be highly correlated. So this is the correlation that comes out of the fit. So how the results, say, correlate to each other when you try to fit them. This is for the first fit that I showed you, so the one from the Ellis group. So linear only, leading order only. And where you see a lot of yellow or blue, it means that things are really anti-correlated or correlated to each other, so the diagonal is blue for reference, and all the greenish means not a lot of correlation. And you see that there are 2 blocks that are really correlated to each other, so this lower left block here is the block of the parameters that go into the electroweak POs, and a bit of Higgs. And the reason why they're so correlated to each other is basis dependent. So this is a feature when you do the fit in the Warsaw basis, because the Warsaw basis is such that in electroweak precision data, you have 2 flat directions. So if you go to z-pole observables at LEP, like 2 to 1 to 2, there are 2 combinations of these guys that you cannot constrain. And those 2 combinations are broken, but a little bit weakly by the diboson measurements, so already LEP2 and also LHC, and by the Higgs measurements. But because the breaking of these 2 directions is weaker than the constraints on the other directions to which electroweak POs are sensitive, basically they remain, so you see a residual strong correlation that was broken only weakly between these two kind of features. Now, if you know where to look at, you recognize also even structures. So they are related actually to that weird operator that I showed you when we were talking about the basis dependence, so that if you have an operator that is not in the basis, you try to write it to map it down to the basis, and you find that from a triple gauge coupling, you get down to a combination of many, many things. So that particular operator that I showed you is actually one of the things that we're blind to in that combination. And so one somehow can recognize that it's really the operators that enter in that combination that remain correlated to each other, because it's not really broken down. Sorry, and the other block is the block of these guys for quark operators in TT bar, because you cannot break them down. So you break them down weakly, so they remain very correlated to each other.
Does this mean that the Warsaw basis is not so good to use the counter-variable studies and search for a better basis?
Yeah, but it's not, I mean, change for a better basis, then change the anomalous dimension matrix, change the matching, change, So, I mean, rotating this thing, if you work with linear terms, rotating this thing is trivial. You just rotate it. There's one thing that you can do actually that, okay, this is going to partially answer your question. Maybe, yeah, no, I don't really have it here, but okay. So one thing that you can do is post-fit, but this is a fit dependent, so it's not a universal basis choice. It's just whatever comes out of your particular fit. You could do something called the principal component analysis. So essentially, you have a chi-squared, right? So when you do the fit, you are minimizing it. So the values of the Wilson coefficient that you're finding there, the central values are the minimum of the chi-square. And then you're identifying the confidence region by whenever the delta chi-squared is equal to some number, okay? Anyway, so you have this function that you have to imagine is 34-dimensional, right? So it's like a 34-dimensional object that has a minimum. You can sit in the minimum and take the Hessian in the Wilson coefficient, so the second derivative around the minimum. So this will give you a sense of the curvature really, really close to the minimum expanding around it. And you can diagonalize that matrix. If you do so, it means that around the minimum where you are, you can basically decompose your fit into another set of, if you have 34 operators, so it's 34-dimensional, you can have another set of 34 dimensions that are orthogonal to each other. So they are, sorry, not orthogonal, but that are uncorrelated from each other. And that is, yeah, so it's basically the diagonal basis of the fit, okay? So you have the chi-square, you go to the minimum. In principle, you have a weird shape in all these directions, but locally you can diagonalize, so it means that you are decomposing your fit into a set of 34 uncorrelated constraints, which, however, are not aligned with the basis necessarily, okay? So if you do this with linear terms, this exercise is particularly clean because your diagonalization, so the Hessian will be independent of the Wilson coefficient. So if you have only linear terms in the prediction, the Hessian is quadratic exactly. Sorry, linear terms in prediction. The chi-square is quadratic, so the Hessian is a numerical matrix. So you can diagonalize it, and it's exact. If you have quadratics, it's a bit more complicated because then the chi-square is quartic, and the Hessian will still depend on the Wilson coefficient, so you have a different Hessian at different points. This is linear, so this is quite safe. And so what they do is that, so basically here you have the eigenvalues of your Hessians, which is a measure of how strong each of the 34 components diagonalized are. And then here in colors, you have the composition of this eigenvector in terms of your basis of Wilson coefficients. So for instance, the strongest bound that they find when they diagonalize the thing in their fit is something that has a CHWB, a CH box, no, I'm mixing up the lines. It should be a CHW and CHB, if I'm not wrong, component. And then they can even tell you what kind of measurements dominates this kind of constraint, so which class of measurement this comes from. And it comes 50% from the simplified temper cross-section, so Higgs measurements, and a bit of run 1, run 2, but still Higgs stuff mostly. And you can, I mean, if you know what you're doing, you can recognize that this is basically the Higgs to gamma-gamma combination. It's a very safe guess, okay? So the strongest constraint that they have is the Higgs to gamma-gamma. The second one that comes here, now I need to follow the line because I'm very confused, is CHG. So the second one here is gluon fusion. And I told you these are the only two that really compete with electroweak precision data. Then from the third on, you have a chunk where you have weird combination of things, and you cannot really isolate which kind of measurements this come from. It's a superposition of different things. But you can look at the column here, and you will find large numbers in the electroweak PO things. So there are a few lines, a few constraints that come from 99, 95, 60, 70% from electroweak POs. So because you have flat directions, this is really mixed up together, but this is Z-pole observable that comes next. And then on the lower corner, so the weakest constraints that you have are those that come from top in the combination of the 4 quarks. So this is really the statement that the weakest thing that you are doing in the fit is distinguishing these guys from each other in TT-bar production. And this sits here. While, okay, there is a combination that is more strongly constrained, so there are some combinations that sit here, but then breaking down the components is there. And it's interesting to see, you don't read the numbers, but that the strongest constraint already reaches into the 20 TeV if you want to express it in terms of lambda. So you say, I have a C over lambda squared constraint. I say the C is equal 1, and I interpret the bound just in what is lambda. So for Higgs gamma gamma, here it's around the 20 TeV if you read the scale. And if you read it for the lowest, this is 200 GeV, so it's barely valid in terms of EFT. And there are 2 orders of magnitude between the strongest and the weakest constraint, which is another typical features of this fit. So you have very large hierarchies. When you sample the likelihood, this complicates things quite a bit between certain directions that are very tightly constrained and some others that are constrained like 2 orders of magnitude later. This, okay, it's a bit more about analyzing the constraints. This is not needed. Yeah, okay, see, this was analysis. Okay, I made a mess because I was preparing this late. Okay, so that was really the last thing that I wanted to say. I can add, but I didn't have time to prepare the slide, but that the experimentalists are also doing this quite a bit. So you have papers by Atlas and CMS that now contain very sophisticated analysis. There is one that just came out for EPS, so a month ago, by Atlas that is the Higgs combination, and they do some very sophisticated stuff. So the advantage of having the experimentalists do this exercise is that they know their correlations, and correlations among measurements are very important in this game. So if you change them by a little bit, your fit result kind of moves around the space. They also have big machinery to do predictions. So they are doing this kind of analysis so working in different directions. The thing that is difficult for the experimentalist is to do the combination, okay? Because the experiments traditionally, they are organized in sectors. So you have the Higgs group, the standard model physics group, and the top group, and they have not worked with each other a lot. It's really a sociological issue. Well, sociological, also technical. So, I mean, they had to divide somehow. They divided in this way. And the result is that some frameworks or some simulation setups, some things are different across the thing. So if you want to do a combination of the measurements in one unique framework across sectors, it's a bit complicated. But they're moving in that direction, let's say. So combining Higgs and electroweak, Atlas already has a combination of Higgs and diboson. CMS, I think, is going around there. They also started from different points. CMS did more top quark at the beginning. But yeah, so things are moving, and eventually the idea is that they can do something like this by themselves internally up to some point that is useful. Yes.
Combination now make me thinking that at the beginning of the lecture you say that it's important the running.
Yeah, sure. I mean, no, this does not have any running. Also, the other thing does not have any running. I mean, okay, running is the next chapter. So you need to have the technology to do it. So it can be important. It's hard to tell. So for the electroweak part, maybe not too much. I don't know. I cannot really give numbers or quantify for that. For the top, we have that paper. So we know what it is for certain things. For the other observables, I don't know. But yeah, so the running is something that, you know, once you have the UFO that can take care of it, you give it to the Atlas people and they run the hell out of it and they will use it. So they really want to use things, but we have to provide, and many of these things are still under development. Yes, so I think we can close it here, and if you have any questions, I'll happily take them. It's hard. So the thing is that All right, so when we think about this like on a global scale, typically you have in mind the Halloumi predictions. So by the story of back of an envelope calculation, this should be a few percent to 10% effect. That is the error bar that you want to have on your measurement, so putting together experimental statistics, systematic theory, uncertainty on the standard model, on a bunch of measurements. Then it depends on where the new physics hides. If it hides in Higgs to gamma gamma, we could find it tomorrow. If it hides in TT bar, I don't know. Well, up to the 5%. No, sure, yes. But it's so, I mean, I think that, so one of the issues that are kind of, ignored so far, because that's the best that we can do, is really the precision of the measurement. So like this program is designed for precision physics and the LHC is not quite there. So LEP is still dominating this thing. So until we don't have that, it's hard to say, okay, we realistically find something. But there are a few isolated cases in which this thing can happen. So I don't expect to find the giant energy enhancement in the tail of something crazy. If you ask my personal opinion. But yeah, it's. Oh yeah, that's. No, sure. Yeah, I mean that's the. No, yes. So okay, that's an NLO issue, but yeah, no, I totally agree. So like the thing that is most worrisome is that like after you find an anomaly, get it right. And there's even people. I mean, it's not my personal opinion, but that in the community there is also the feeling of like, the day you find an anomaly, you're gonna just put simplified models in it, like the 750, for instance, or like the B anomalies. You just put the leptoquark and you try it out. And this framework is not necessarily the simplest setup in which you want to do it. If you have a set of anomalies, then this can be more interesting because it relates things. There will be a bit of both, I guess. I don't know. It's hard, hard to tell. Yeah.
On slide 28, and I think also on 30, you had some weird operator at the end of the boson line. The yellow.
Sorry, yeah, it was indicating the decay. No, it's in the sense that then if you decay the W and the Z, then you have the leptonic guy or quark guy, or like in general that also decays, right? So you can have stuff there.
So yeah, that's Professor Brivio again.
Thanks.